Hey guys, I am here to talk about the fundamental theorem of calculus, which is probably one of my favorite theorems in all of calculus. It's just incredibly beautiful how you can take a derivative which models rates of change and relate it to the integral which models area. It's pretty crazy. We talked some about this last time when we looked at the velocity and we built kind of the antiderivative of velocity as the area underneath the velocity curve. So now we actually have this big theorem that really relates the two. So the fundamental theorem of calculus has two parts. So I kind of broke it down for you in terms of words first. So the first thing that I said for part one is where we take an antiderivative and we use it to construct a definite integral. And then part two, you kind of go backwards. This is where you use a definite integral to construct a function that will model the area that's actually your antiderivative. So I've given you the first fundamental theorem of calculus right here. So this just tells us that if we take a definite integral, which will calculate the area underneath this curve f of x between a and b, some interval, then this is just the antiderivative of f of x of little f evaluated at b minus the antiderivative of little f evaluated at a. So there's actually some neat things that we can do with this. We're not really going to talk about these today, though. I'm mainly going to focus on the fundamental theorem of calculus part 2. And this tells us that we can actually write a function that will model area. And we'll call this an area function. And we can write it as a of x. Sometimes I write it as capital F of x. Just depends what you like. And so now we can take and our independent variable in this area function is going to be our upper limit of integration. So we have a function that will model this area, and it's really based on that upper limit. So one neat thing that this does is that it kind of relates the derivative and the integral and shows that they are inverses of each other. So this is another really neat part of it. So this tells us that d dx, which would be the derivative with respect to x, of this area function is equal to our original function f of x. So a lot of the questions that are asked are just kind of conceptual regarding the fundamental theorem of calculus part 2. A lot of them just want you to kind of take the derivative of an integral and see what you get, which a lot of times just entails, taking this upper limit of integration x and plugging it in for whatever variable that they've defined f under. Another thing you can look at is if you actually, instead of having an x as your upper limit, if you have an f of or some function. And generally questions like this will ask you to take the derivative of your integral. And so then you do something very similar to what you do. You plug this in, this g of x in for t. But kind of, think about what happens when you take derivatives. You also have to deal with the derivative of your inner function. So I call this the chain rule for the fundamental theorem of calculus. So if you have an upper limit that is not just x, and its derivative is not just 1, that's really what you're interested in, is the derivative of g of x1. If it is, then you just plug in what's up here. If it's not 1, then you plug in what's up here for t or z or whatever it is, and then you have to multiply the outside by the derivative of g. So let's try some examples where we work with this second fundamental theorem of calculus. So here, I've given you a couple easy ones. So it's really important to read the instructions, because if I just saw this right here, I would probably, start scratching my head and trying to figure out how to integrate sine squared of t over t, because we really don't know how to do that. But then I, go back and I read the instructions like I'm supposed to, and I see that they want me to find f prime of x. and I've defined capital F to be this area function right here. So I really am wanting to take the derivative of this. So the derivative and my integral are inverse functions of each other. So what I need to do is I need to use this second fundamental theorem of calculus, and it tells me that these will cancel each other out. Now, one thing to think about is your lower limit. Your lower limit always needs to be a constant, and your upper limit always needs to be a variable or a function defined in terms of a variable. So let's go ahead and let's use the fundamental theorem of calculus and see what it tells us. So it tells me that this thing is going to be equal to f of x. So really, I just need to plug in x for all my t's. So this is equal to sine squared x over x. There's no need to deal with the constant down here or to look at what happens when sine squared t over t is 0, because if you really were to integrate this function right here that I have, and you were able to, when you took the derivative, because that's what they're asking us to do, is take the derivative, the constant at the end would fall out. So there's no need to even mess with it. All right, so let's take a look at another example. On this example, all we want to do is we want to rewrite it so that we have a constant on the bottom and we have our variable on the top. So we want to use this property that tells us that if we flip our limits of integration, that we can do that and then just put a negative sign on the outside, and it will kind of counteract each other and they'll be equal. So now my lower limit needs to be 2, and my upper limit needs to be x, and then I've added this negative sign to the front. So now I can attack it using the second fundamental theorem of calculus. I'm just going to take my x and plug it in for all my variables. The derivative of the x is just 1, so I don't have to worry about multiplying by 1. So this is going to become x cubed minus 1. For the last one, I've given you one where you do not have, the derivative of your upper limit of that g of x is not equal to 1. So let me show you how this is going to work. So you're still going to take this upper limit and you're going to plug it in for t. But what you're going to do is you're going to have to take cosine of x squared cubed, and multiply the outside by the derivative of your inner function, which is going to be 3x squared. Oh, yeah, no, that's it. And so that's it. So you just make sure you remember that your variable has to be on the top and your constant has to be on the bottom. Don't worry about plugging the constant in. Since you're taking the derivative, it's going to go to 0. It's just going to be 0 anyway. And then the last thing is that if your upper limit right there, remember, is a function whose derivative is not equal to 1, then you have to multiply the outside by the derivative of that upper limit. Okay, so let's talk about interpreting graphs using the fundamental theorem of calculus. So this is a really big AP topic. They really like to give you a graph of a function and ask questions about its antiderivative. So I really think that the easiest thing to do in terms of these questions is to just think about the fact that the derivative of capital F, so when they ask you questions about capital F, you have to think about the fact that you're looking at the graph of its derivative. So since we know from the fundamental theorem of calculus, if we differentiate both sides of this integral right here, we're going to get that f prime of x is equal to f of x, just exactly those exercises that we just did. So this is what you want to think about. You also can get questions like part A, where you actually have to take and shade some like shade in the area and calculate the area by hand because obviously you don't have an equation for this graph. So let's take a look at what we're given. So I always like to pay attention to my lower limit of integration. So it's 1. So that means that all of these areas that I'm going to be accumulating are going to be starting at 1. So I'm going to draw a line here just to help myself remember that this is where my area is going to begin. And then always remember, I like to mark my x-axis too. In this picture, it's kind of hard to see that any area below this x-axis is going to be negative. Any area above it's going to be positive. And then always remember, if you're accumulating area if to the left, then it's going to be negative. If you're accumulating area to the right, then that's going to be kind of positive. Make sure that your upper and lower limits, the lower limit is on the bottom and the upper limit's on the top. Now you got to kind of flip your signs around. So let's go ahead and start these integrations. Get a thinner pen. So we want f of -1. So what this is going to be is I'm going to start at 1 and I'm going to accumulate area to -1. So I want the area between the x-axis and the curve. So that's going to be this area right here. And now you just got to use formulas. So this is going to be the integral from 1 to -1 f of t, f of x dx, I guess. I guess it's t, but whatever. So I need to make sure that my lower limit is on the bottom and my upper limit's on the top. So I'm actually going to rewrite this, and I'm going to put that negative sign in front. So it's going to go from -1 to 1. And then now I actually want to see how I'm going to calculate this area. So I have a quarter of a circle. My circle has a radius of 2. So this is going to be -1/4 times 2 squared. But I also forgot something. I forgot that, I forgot that my area is underneath the x-axis. So I actually end up with 2 negative signs because I'm accumulating area to the left, and that's why I have that extra negative, and my area is below the x-axis. So that's negative right there also. And I forgot my pi too. Man, it's been a long day, I guess. So this is 1/4 times pi times r squared. So this is 4 and that's 4, so those are going to cancel, and then the negatives cancel, so my answer here is just pi. Alright, so now let's take a look at f of f of 3. I'm kind of short on room, so I'm going to erase and do the next part. F of 3, so I'll do that with blue. So now I want to accumulate area from 1 to 3. So now I'm actually accumulating area to the right, so I don't have to worry about flipping my limits of integration. And I have a true triangle. So this is going to be pretty easy, I think. I know the formula for a triangle. So let's say this is the integral from 1 to 3. I'll write it correctly this time, dt. And this is going to be equal to 1/2 base times height. So the base of my triangle is 2, and the height of my triangle is 2. So that's 2 times 2. So that's just 2. The area is positive. It's above my x-axis. So that one's pretty easy. So let's try the last one. So this is also, so now this is 1 to -3. Integral from 1 to -3. And so I have f of t dt. So once again, I have to flip my limits of integration. So my lower limit's on the bottom. And then I want to look at this area. So this now is going to be from 1 to -3. So now I have a semicircle, half a circle. So the circle has a radius 2. So this is going to be negative. It's going to be negative again because it falls below the x-axis. And then this is going to be 1/2, right, times pi times 2 squared. So this is going to be 2 pi. That's my answer. So those are pretty simple. Just pay attention to your lower and upper limits. One thing that I'm really bad about making mistakes on is always starting at the very far left point, like just assuming that my lower limit is -5. And that can get you, make some mistakes that way. Always pay attention to where your lower limit is. So now let's talk about concavity increasing, decreasing. So they're asking me questions about capital F. So I have to remember this is the graph of little f. Little f is the derivative, sorry, f prime of x is equal to little f. So this is the graph of my derivative. So this is kind of what you want to continue to think in your head. So if we want to find intervals of concavity, then this is going to be where my derivative is increasing, because that's going to be where my second derivative is positive. So if I look at this graph from -1 all the way to 3, my graph is increasing. So this is going to be concave up from -1 to 3. Because f prime is increasing, which implies that f double prime is greater than 0. All right. On what subintervals of -5 to 5 is capital F increasing? Well, if I'm looking at the derivative of capital F, then this means that it's going to be increasing where the derivative is positive. So it's positive from -5 to 3, and it's also positive from 1 to 5. And this is because f prime is greater than 0. And this is, where does f have a local maximum on the interval from -5 to 5? And so once again, if I'm looking at a graph of my derivative, it's going to have a maximum where my derivative goes from positive to negative. And that only happens one time. It happens right there at -3. So it has a max at x equal -3, because the graph of f prime goes from positive to negative. So these are some really nice applications of kind of the fundamental theorem of calculus, giving this graph of, the original function and looking at the antiderivative. So now I want to kind of switch gears, and I want to talk about, really quickly, we're going to kind of breeze through this, about applications of integration, and how, and if you're given a rate of change, that you can find the net change because it's just the integral. If you're given a rate of change, you want the original function, you can take the antiderivative. So if you want the net change over an interval, then that's just your definite integral. So here we have a formula that tells us the net change of some original function at s of t over this interval is given by this expression. So we'd have to be given a rate of change. And then what we want is we want to integrate it from our lower to our upper limits, and then that's just going to be the net change over that interval. So here we have one that's pretty simple. So we have water leaks for the take at a rate of 5 plus 2t liters per hour. How much is lost between 9 and 11? And my hour starts at 7. So this is going to be from 2 to 4 if it's 9 to 11. So I just want to integrate from 2 to 4 my function for rate of change. My function for rate of change is 5 plus 2t. So I integrate from 2 to 4. This becomes 5t plus t squared from 2 to 4, which gives me, let's see, 5 times 4 plus 4 squared minus 5 times 2 plus 2 squared. So that's 36 minus 14. So I get 22 liters is how much water I have lost between 9 and 11. All right, so let's try it with Riemann sums. Same deal. So at first they ask, we have the number of cars passing per hour is given by Q of t. So this is a rate of change. And then the first thing they ask me is what quantity is represented by the integral from t1 to t2. And so this, just like, it's your net change. So it's going to be the total number of cars that passed between T1 and T2. So now they say the flow rate is recorded at 15-minute intervals between 7 and 9. Estimate the number of cars using the highway during this 2-hour period. Generally, when they give me a table and they ask me for an estimate, I'm not going to pick left or right. I'm going to do probably trapezoid or midpoint. I think I'm going to do trapezoid here. So I'm going to find left and right, and then I'm going to average the two. So I'm going to do left. I have 1, 2, 3, 4, 5, 6, 7, 8 intervals. It's nice that they're in 15-minute increments. So since my Q of t is given to me in cars per hour, I also want my time to be an hour. So my time increments are 1/4 of an hour. And now remember, with left, we're going to include the first point, but we're not going to include the last point. So this is going to be 1044 plus 1297 plus 1478. You get the drift. And then we add all the way up until the next to the last point. And then once I've multiplied added all that together, multiplied by 1/4, my left sum is going to be 2612. So since I want, a best approximation generally, I'm going to do the right sum, and then I'm going to average the two. So my right sum, remember for right sum, I'm not going to include the first point, but I'm going to include the last point. And my distance still, my delta x is still 1/4. So then this is 1297 plus 1478 plus dot, 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 all the way to 542. And then my right estimate is going to be 2487. So now I want best estimate. So I want the trapezoid, which is going to be my L sub 8 plus R sub 8 over 2. So this is 2550. So then I'd probably, write a sentence. Approximately 2,550 cars passed between 7 a.m. and 9 a.m. So another application that we can look at whenever, as we look at, the integral of a rate of change is looking at the integral of velocity and trying to determine displacement or total distance traveled. So we kind of have two ways that we can do it. We can look at displacement, which is just going to be the distance from your starting point. So think about velocity, right? Velocity is the rate of change of distance. So if I find the antiderivative of velocity over an interval, it's just going to tell me how far my distance is from my starting point, or from T1. The total distance, it's going to tell me the distance between T1 and T2. Now, sometimes you don't want to know how far you were from T1. You want to know your total distance that you traveled, whether it be positive or negative. And when they ask for total distance traveled, you have to look at the integral of absolute value, because you don't want the negative areas to be negative. You want to account for all the area. So let's look at an example. So we have a particle that has a velocity represented by this equation right here. So we want to compute two things. We want to compute displacement over this interval from 0 to 6. and then we want to compute the total distance traveled over 0 to 6. So let's do displacement first. I've included this graph. We'll talk about it when we do total distance traveled. So displacement is just the integral from 0 to 6. T cubed minus 10t squared plus 24t t. So if I integrate this, I get 1/4 t to the 4th minus 10/3 t cubed plus 12t squared from 0 to 6. And then when I plug in 6 and I do the math, I get that this is approximately, it is 36 meters. So this is how far I am from my starting point. So now let's talk about total distance traveled. So it's really helpful when you're trying to determine total distance traveled to look at a graph, because I don't want to take the antiderivative of an absolute value function. It's much easier for me to just look at the graph. So I've given you a graph right here and say, okay, all this negative area just needs to be flipped up and put above the x-axis. So what we end up doing is we take this negative area wherever it hits the x-axis, so wherever it's equal to 0, and we just change the sign. And so we actually split it into two integrals wherever the function crosses the x-axis. So I see, if I can erase all the stuff I wrote, that my function crosses the x-axis at 4, and between 4 and 6 it has negative area. So I need this area to be positive. So for total distance traveled, I want to write two integrals. My positive area is going to stay positive. So this is going to be the integral from 0 to 4 of v of t dt. And now, since this area down here is negative, below between 4 and 6, then I need to change the sign. So I'm just going to make it negative so that it will become positive. And so now I've changed the sign here. So I already know what the antiderivative of v of t is, so I'm not going to bore you with all that. So let's look at the integral from 0 to 4. So if you look at the integral from 0 to 4 and you find the antiderivative, you're going to find that this is equal to 128 over 3. That's this part. And then now we're going to subtract that negative area, so we flip the sign, and the area between 4 and 6 is negative 20 over 3. So now we've made it positive. So this becomes 148 over 3, which is approximately 49.33 meters, is our total distance traveled. All right, so I hope you've learned about the fundamental theorem of calculus and some neat applications of integrals, and I will see y'all later.